Now let's talk about PLCs RTUs. A programmable logic controller is a device that receives input information, inputs, and then applies pre-programmed logic to determine what output actions to take. It started in the auto industry. Back in the day, appreciate with relay logic, the more complex it gets, the more relays. And if you change the logic, then you have to rewire the relays. And at one time in the auto industry, when they went from one model year to another, that was a big deal to do. And the original PLCs were designed to fundamentally allow changes in programming instead of actual physical changes to change the control sequence of the system. Um, Today, once you get beyond a fairly simple panel, like and very often maybe a pressure system with multi-panels, the moment you get into anything more complex, certainly the moment you start talking analog, in other words, varying signals, then PLCs are the way to fly. And PLCs, the ones we dealt with, virtually bulletproof. You say, oh my God, would I trust a computer? No, I wouldn't either. But these things are tough as nails. And in all the years we had them, we had maybe a programming mistake, that's quite possible, maybe a wiring mistake, but never a fault with the PLC. People phone up and say, oh my God, it's got to be the PLC. No, it actually is never the PLC. I won't say never, but we never saw it. And because of their design for industry, I think it's extremely rare to see an actual failure within a PLC. Now, basically, the typical PLC, and they're different manufacturers, but basically has a chassis with a power supply. And there are several slots on that chassis. And they come in different options of how many slots. Into the first slot goes the processor card, which is the brain of the thing, what you're actually programming, and then input and output cards as you need them. Okay. Um, Here's a typical PLC, and I'm going to get off on a tangent for a moment. We used Allen Bradley when they existed, what were known as the SLCs. We called them slicks. Everybody did. And beautiful PLC. It was replaced with, they went both up and down from that, but that original slick was an excellent unit. Little footnote, by the way, what we would do for testing these things is we would actually have them wired up at the control shop and then would test it, the inputs and outputs, which the PLC will show you whether they're working or not. Then we would pull it out and leave all the wiring. The terminal strips on the cards could actually come off quite easily with screws. We'd pull those off and then take the PC into our shop, um, test it out, make sure that we would load the program, make sure the program is working. And then if the site was if it was in driving distance, fine, but very often we're up north and would check it in as luggage in a decent box, get there, take it out, connect it back in again, and work like it should. But basically, looking at this thing, you can see on the left is the power supply, the big darker gray. Then the thing with a key on it, yeah, they had a key, is for programming. That's the actual processor card there. And then from there on, you had input and output cards. And if you here, like we had the main card plus five others, so you had six cards and 7 slots. You could get blank cards. The one on the far right is simply blank. It isn't doing anything at all. And here's a better shot of it. Here's like a four to the right, a four card. First one, or the left, is the power supply. The first card is the processor, and then inputs and output. And they don't have to be in that any particular order. We always inputs first and then outputs, but that isn't absolutely necessary. RTUs. Originally, an RTU was strictly a communication point within a SCADA system. It also had both input and output capability and limited processor capability, but enhanced external communication ability. It was really designed to be a telemetry unit and send signals remotely by radio or whatever. But as time went on, they decided we can expand, we can be the actual controller. And at the same time, PLCs developed with enhanced external communication, so they became effectively also an RTU. So the line between them is blurred. And many people will use either a PLC or an RTU to do both control and communication. Others, me, argue that the ideal approach is to have a PLC handling the I/O and managing control, connected and communicating with a basic RTU for external communications. Then, if the RTU fails, the station's still operating and you get an alarm that the communication has failed. The other direction around, if the PLC fails, you're sure to get an alarm. Programming. Oop, did I miss something here? Nope. Okay, inputs and outputs. Inputs and outputs can be of two types, either discrete or analog. A discrete input is either on or off, true or false as it shows up in the program. Analog is a varying signal, and the classic is a 4 to 20 milliamp signal. We'll get to that in the next talk about, or further on, about 4 to 20 milliamp signal, which is quite common as a voltage signal, where the output can be anywhere between 4 milliamp and 20 milliamp. And they're saying here, one of the things, why to use 4 to 20 instead of 0 to 20? Because if the signal fails, you'll classically have an alarm anything below 2 milliamp, and you know something, the signal has broken, and that can be fired off as an alarm. And we'll get to, again, further the thing about using using milliamp current instead of voltage. The conductor resistance doesn't become a factor. That's sort of an early introduction to something we'll get into later. Now, programming these things. There are several possible approaches to program logic into a PLC. An IEC standard 1131-3 defines 5 different program languages. Ladder diagram, function block diagram, you can read them. In North America, ladder diagram is by far the most common because most people are familiar with relay logic. So pretend the others don't exist. Now, let's take a look at a typical setup. Let's say we have a start and stop float switch like we were talking before. Stop flow switch, start flow switch, and they are connected up so that they are inputs. And by the way, for some unbeknownst reason, PLCs and RTUs, the first is always a 0. So input 0 is the start flow switch. Input 1 is the stop flow switch. Similarly, outputs, and in our case it was the outputs to the run light and the starter, that can be done with a single output because of the same thing, and it's output 0. Okay? And the output cards, you can get them either with a common relay, as we're showing, where there's several of a common power supply. You can have an individual relay, so each relay has a slightly different power supply. Or you can have triacs, in other words, solid state if you want to go that route. I like the relays because they're easy to understand and fairly basic. Now the program. And you program these things with a PC or whatever, and the programming software that's needed to do it. And basically you start putting it together, and it's not that hard once you kind of get used to it. Program, you do it on the computer, and then you simply, when you got it and you're happy with it and it's doing what you expect, then you download it to the PLC, and the PLC immediately will follow what you've told it to do. Now, the one thing the PLC does different from ordinary power supply, it actually does it in scan, line by line by line. And we'll show you how. You can see this thing wired. There's the on 0 is the, or ON0, it's card number 1. That's what the number at the top is. Card number 1, and the input is 0, and that's the stop flow switch. The next one is the start flow switch. And instead of relays, they call them bits. There's the bit, and it's not getting a power, so it's off. There's its latch bit shown below, and another bit, because we're calling it latch. You can title these things anything you want. We're calling it latch bit. Is actually the one that goes over to output 0, which is powering the light and the starter coil. And then there's an end, and the end is because this thing works in scan systems. I'll show you. Okay, so the PLC comes along the dotted line to the first rung, comes across and says, nope, I can't cross that, that's open or false. We come across, then it goes down to the next horizontal line. I can't go anywhere with that. I then go down to the one at the bottom. It says end. Well, since it's end, I start again. So again, I go to the first one, the second one, third, and it's cycling, obviously, very, very, very quickly. Okay, fine and dandy. Now, here's our example. We've set it up, and the way we're sitting right now, nothing is happening because the two float switches aren't floating yet. Now, okay, the stop float switch has tilted. Its input is now true. So the scan line comes along and says, oh, I can go through here now. Whoa, I can't go to the start float switch. That's false. The latch bit is false. Next line I can't go through because there's a false latch bit. Go to the end, and I'll start this whole little game all over again. Fine and dandy. Now the start float switch has floated, and its input is true. So the scan line comes along and says, okay, fine, I can go through the stop float, input 0, ON 0. I can go through ON 1 now, and I can go to the bit, I can turn it on, which then make the other two contacts for it true. Fine and dandy. I'll go down to the next line, come along, that latch bit contact is true now. I can go over, I can energize output 0, which puts on the light for the motor and the green light for the motor running and the actual motor starter itself. Hit the end, do the same thing all over, just keep doing it. Now, the level comes up, start float switch is false now, so the scan line comes along, goes through, hits that false start float switch contact, can't do anything, but it follows down on the next subline and it sees the latch bit is true. I go over, and so I don't touch that latch bit. I keep it energized, okay, or keep it on. Go down to the next line. Again, that latch bit is there, so I can go on. So the output to the light and the motor starter are there. And the thing keeps running. Then I go to end, and I start the whole scan line all over again. And finally, when stop float switch is no longer an input, so that its bit is now false, scan line comes along, I can do nothing there. And because the scan line can't get over, the last latch bit falls out. Okay, goes back to fall. And so down the latch bit contact is false, it's open. Power to the motor and light go off, so the pump stops and the light goes off. And then we start this whole little scan process before. Now, this is a copy of an actual program PLC printout. The elements are selected by the programmer that are going to go into the thing, automatically labeled. Text above where the light scanning in the back. You can call them whatever you want. Like here again, we decided to call it stop float switch, next one start float switch, latch bit. Those titles we can put on ourselves. The rest of the labeling, the PLC will kind of do it automatically for you when you clip into it. And there is your program. And does that ever look familiar? Okay, so it's that. It can be that simple, but boy, can they do a whole lot more than just that. Now, analog signals. And to say analog signals, the classic is a 4 to 20 milliamp signal. At one end of the scale, 4 milliamp and 20 milliamp. The PLC doesn't and can't directly handle that. But what it does, it'll have an analog input card that converts that to numbers. Okay? And for example, if a PLC analog input has a 14-bit resolution, which is 2 to the 14th, that's a grand total of 16,384. So 20 milliamp, in other words, a full 20 amp signal coming in to the PLC becomes 16,384. It's a number in a file. And the 4 milliamp becomes 3276. So you're operating between these two numbers. And any value in between becomes a number. PLC then uses program logic to arrive at an output number that a PLC card will take the output number from the program and convert it back into an analog value. Okay, so you can run a variable speed drive or whatever from it. For example, if we assume we have a sump that's 3 meters deep and want to start a pump at a liquid level of 2 meters and pump it down. Also assume we have a level monitor that provides this 4 to 20 milliamp signal, and a liquid depth of 0 is 4 milliamp, and a liquid depth of 3 meters becomes 20 milliamp. The analog input card will convert this analog input signal to a number between 3276 and 16384. And I'll show that a bit. I'm reaching a set put signal of 2 milliamp. The value will be 12107. 1460 milliamp if it turns into 12017, pardon me. PLC will then simply be programmed to start this pump when it reaches 12017. Now, here's what we're talking about with when I noticed 017, the 0 and the 1 got crossed. So at the bottom end, the level sensor is going into the input card at 4 milliamp. If the depth is 3, it's going in at 20. That's our range. And we want to start the pump at, say, 2 meters, which is 1467 milliamp. The PLC converts that to numbers, as you can see, and the critical number here is 12017. When it hits that number, then it will know to start the pump. The high or control, if it's variable speed, it will control at that level if you've set it up that way. Now, the higher the resolution, the more accurate the values are measured. For example, with a 30-meter tall water tower, which is about 100 foot, I remember this very first time I ever dealt with a PLC. It had 8-bit resolution. That means 2 to the 8, 256. There, each count, the difference between 255 and 256, each count was an equivalent in height of about 146 millimeter, which is about 6 inches. And we actually had a program where, start this pump at this level and go one count down, and, we're 6 inches lower than we do something else. The numbers actually did mean something, but the finest you could get was 6 inches. However, with 14-bit resolution, 2 to the 16384, each count is equivalent on the same water tower, 30 meter tall. Each level count is equivalent to 2.3 millimeters. Well, 2.3 millimeters is, like less than a quarter of an inch. If you go to 15-bit resolution, you're down to 1.1 millimeter. It's like they say, like a pixel count on a digital camera. The more pixels, the sharper the image. But here, the higher the resolution, the more accurate the value. Communication, and this is getting into a dream world, but at least something I wasn't heavily involved in, but at least understand the basics of it. More and more common for equipment to communicate discrete and analog signals by means of buses, digital buses, digibus, or field bus signals, carried over cable lines, fiber optics, or even over radio. This thing about packaging signals greatly reduces the cabling required while permitting large amounts of information to be conveyed. There are many communication languages. Two most common are Modbus RTU and DeviceNet. Modbus RTU was developed originally by Modicon, which developed the first PLC. Modicon was bought out by Schneider a few years back. The second was developed by Allen Bradley, which Allen Bradley now part of Rockwell, who also make PLCs. And both became open protocols that any manufacturer may incorporate in equipment. It's like the old thing with Sony Betamax. If you hold it for yourself, nobody except you will use it. So it's advantaging to have it open. The one thing about DeviceNet that is kind of cute, it's based on the CAN bus controller area network system developed for automotive use. Appreciate in a lot of cars now, instead of having wires going back to turn on the brake lights, they have a single communicating line that tells the unit the light will have power and a switch, and you send a signal back that says turn on the brake light, and it does. Doing it that way, you don't have individual wires for each light and sequence. You're basically sending information packages to activate. And because it's designed for automotive use, it's cheap because the volumes of production are huge. And with DeviceNet, the messages are sent by means of an 8-bit format of letter numbers. And you can see like 3E, 80, D1, BF, FF, E2, 9E, 00. That's an 8-bit message that is fired back. And when the device reads that, it knows what to do. An interesting example of this, I said a recent article, well, a few years back now. We're talking about swapping a 376 LS engine into a late model Mazda Miata. And the trouble is, of course, that the engine had its CAN bus system, but with its own meanings for what each signal was. And Mazda had their CAN bus communication system for the rest of the call, but the two couldn't talk. So they put together what is known as a gateway box, which the guy's holding in his hand. And what it does, if there's a signal coming from the engine, it translates into Mazda and sends out the code for Mazda. Similarly, if Mazda is trying to tell the engine something, it takes that signal and flips it into GM talk, and away we go. And that allowed them to, once they developed that very fancy little box, the thing just plugged in and away it went. Programming advice. Use caution when offering a range of settings to the operator. Bad things can happen when a value is selected that is beyond what was envisioned. For example, let's say you figure the guy will be operating, I don't know, a level between 3 and 10. And you say, well, he'll set it at whatever. And let's say the operator, and he sets it at 0. That can pose a problem. The control reactions can be something you didn't expect. It's quite easy to do that in programming. Basically, if you can have a function in the program that basically says, if you're below 3, you substitute 3. And it's kind of funny. I've actually played with them. You'll set a lower one, and you can see there's a fraction of it, and the setting will go to that for a fraction of a second, and boom, it goes back to 3. Very cute. So we've had some problems with that now. Behold the turtle. He makes progress only when he sticks his neck out, and I hope you've enjoyed this introduction to PLC RT use.